We are going to continue talking about transient analysis of first order circuits today. And I am going to begin with a little bit of review from what we did in our last class meeting. So that we can introduce a new concept. So we kicked off our last class meeting by looking at RL circuits. So I'm going to draw here a simplified RL circuit. So let's say that we have some resistance R connected to some inductance L, like so. And then over here, we'll have a current source, and we'll make this B. And our switch was closed at A or closing at B at T is equal to 0. We analyzed circuits like this, and what we found was that our inductor current IL of T was of the form IL at 0 minus for T less than 0 minus, and it was IL at 0 plus e to the negative R over L T for T greater than or equal to 0 plus. And after looking at the consequences of this result by applying Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law, we generalize this to say that Y of T, where Y is any voltage or current in our system, would have the form of Y at 0 minus for T less than 0 minus, and Y of 0 plus e to the negative R over L T for T greater than or equal to 0 plus. After we figured this out and worked a few example problems, we then took a look at RC circuits. So a simple RC circuit, I'll put over here on the right-hand side, might look something like this, where we have a voltage source connected to a switch. This switch is going to open at T is equal to 0. We have our resistor R here, our capacitor C over here, and this will be our voltage VC as a function of time. Let me draw that C a little bit better. And we found that VC of T was of the form VC at 0 minus for T less than 0 minus, and VC of 0 plus e to the negative T divided by RC for T greater than or equal to 0 plus. Again, looking at the ramifications of this by applying Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law, we could generally say that y of t, where y is once again any current or voltage in a first order RC circuit, would have the following response: y at 0 minus for t less than 0 minus, and y of 0 plus e to the negative t divided by RC for t greater than or equal to 0 plus. So we surmised that RL circuits and RC circuits behave in effectively the exact same way. The only real difference is this bit here that's being multiplied by our variable t. Other than that, the behavior is exactly the same. So people much smarter than me came up with the idea of a time constant to formalize this rate of decay for first order circuits. Okay, so effectively, if a circuit is decaying at some particular time constant, it does not really matter if we look at it as an RL or RC circuit. We're just looking at its exponential decay. Okay, so let me talk very briefly here about the concept of time constants. So the time constants are what quantify the rate of decay of one of these systems. So for those of you who are familiar with chemistry and things like that, it's similar, but not the same as kind of the concept of a half-life for the amount of time that it takes a radioactive material to decay by half of its initial quantity, right? So a time constant is defined as how long it takes an electrical signal to decay to about 37% of its original value. You might be saying to yourself, well, 37% seems like kind of an odd number, and it definitely is, but it's rooted in a simple mathematical definition, okay? So the time constant tau is the amount of time needed for an electrical signal, so either a voltage or a current, to decay to its original value. Let's call this y at 0 plus to e to the minus 1, or approximately 37% of its original value. So we can make a simple table here. On the left-hand side will be time, and on the right-hand side will be y of t divided by y of 0 plus. And in 1 tau, we will decay to e to the minus 1. Just let me get my calculator here. Is 36.788%. Okay. In 2 time constants, it'll decay to e to the minus 2, which is 13.534% of its original value. In 3 time constants, we'll have e to the minus 3 or 4.979%. In 4 time constants, we'll have e to the minus 4 or 1.832%. And in 5 time constants, we'll have e to the minus 5 or 0.674%. We're going to stop here. So we stop here because after 5 time constants, our signal has decayed to less than 1% of its original value. Okay. So if we were to plot something, it could be a voltage or a current. Here's Y. Here's T. After 5 time constants, our value is effectively 0. So when I was talking on Thursday about T is equal to infinity, as engineers, we can't really look an infinitely long distance into the future. Well, 5 time constants is really good enough for us for infinity because the capacitor or inductor has effectively become fully discharged for all intents and purposes, right? So 5 time constant is what our infinity means in our analysis. We have completely de-energized our circuit or discharged our energy storage element, okay? So in terms of time constants, we can easily see then that for an RL circuit, our time constant tau is simply equal to L over R. And for our RC circuits, our time constant tau is equal to R times C. So using the concept of a time constant will ever so slightly change our general form and the steps that we were using to solve circuits. Okay. So let's outline this new procedure. So here's going to be an example. Let's work an RC circuit because we went through the one that we looked at rather quickly in our last class meeting. So let's say that we have a 10-volt source, a 4-ohm resistor, a 6-ohm resistor, here's our switch that's going to open at T is equal to 0. Put a 5-ohm resistor here, a 3-ohm resistor here, 60 millifarad capacitor here. And just for the sake of argument, let's put a 12 ohm resistor over here. And let's say that we are interested in the voltage drop across our capacitor and the voltage drop across this particular resistor. Okay. So our first several steps for our analysis are going to be the exact same thing that we saw last Thursday. So step number one is still going to be to analyze the circuit at t is equal to 0 minus. So at t is equal to 0 minus, our switch is closed and our capacitor is an open circuit because we're at DC steady state. So that means I can redraw my circuit as this guy. Four, 6, short circuit here. 5, 3. Here's my capacitor represented by an open circuit. 12. And this will be VR of 0 plus. This will be VC of 0 plus. So anybody have any thoughts on how we might solve for either of these quantities? All right.
Well, we need, sorry, I was just gonna say, it's kind of trivial, maybe, we need to find our current first. So maybe we'd use nodal analysis.
We could definitely use nodal analysis and solve for both of those voltages directly doing that. So let's go that route. Okay. So I'm going to identify my nodes. I am going to choose to put my reference or ground on bottom. I'm going to call this A, B, and C directly. Actually, let's change that. It'll be slightly confusing that there will be two VCs, even though they literally represent the same thing. But let's call them VX, VY, and VZ, just so that we aren't using the same quantity twice. So if I'm doing nodal analysis, I don't have any dependent sources or anything like that to worry about. So I don't have any controlling variable equations. I have a voltage relationship equation that says that Vx is equal to 10 volts. Performing KCL at node Y is going to give me Vy minus Vx over 4 ohms plus Vy over 6 ohms plus Vy over 5 ohms plus Vy minus Vz over 3 ohms. Set this equal to 0. So just to be clear here, all I'm doing is I'm adding this current, this current, this current, and this current with those indicated directions together. I'm going to have a KCL equation at node Z where I'm going to add this current and this current together, there will be no current flowing down through the capacitor since it's an open circuit. So that's going to look like VZ minus VY over 3. Plus VZ over 12 ohms. And I'm going to solve this system. Vx is obviously going to be 10 volts. Can't do Vy and Vz in my head, so give me a moment to throw this into a calculator. So 3x3 system, my coefficient for Vx in my first equation is 1, then I have 0, 0, and 10. My coefficient for Vx in my second equation is negative 1/4. My coefficient for Vy is 1/4 plus 1/6 plus 1/5 plus 1/3. Let's see, 1/6 plus 1/5 plus 1/4 plus 1/3. We got all those together there. My coefficient for Vz is negative 1/3. Constant term is 0. In my second equation, third equation, my coefficient for Vx is 0. My coefficient for Vy is negative 1/3. My coefficient for Vz is 1/3 plus 1/12. So if I've entered all that into my calculator correctly, I get Vx is equal to 10, Y is equal to 150 over 41. And Vz is equal to 120 over 41. And by inspecting our circuit, we can see that VR is just Vy minus 0. So this is VR at 0 minus. And similarly, Vc is Vz minus 0. So this guy right here is just Vc at 0 minus, and we've used nodal analysis to determine both of those voltages. Nodal analysis wasn't incorrect to use here by any stretch of the imagination. I personally was leaning more towards using voltage division to find VR. And then once I found VR, I could use voltage division again to find VC. So we'll just run through that very quickly as a brief review on voltage division and also to make sure that I didn't make any mistakes here. So I would say VR of 0 minus is going to be 10 volts. And then in my numerator, I want the resistance that I'm trying to find the voltage drop over. So I see 6 in parallel with 5 in parallel with 3 plus 12. So let me write that here. So that's going to look like 1 over 6 plus 1 over 5 plus 1 over 3 plus 12. Take the reciprocal of that to give me that equivalent resistance. And then down here in my denominator, I'm going to have the total series resistance, which is just 4 ohms plus that same large equivalent resistance there. So if I throw this into my calculator, let's go to the right mode here. So 1 over 6 plus 1 over 5 plus 1 over 15. All that to the negative 1 power is 30 over 13. So I'm going to have 10 times 30 over 13 divided by 4 plus 30 over 13 gives me 150 over 41. And then I can find VC as VR of 0 minus times 12 over 3 plus 12. So times 12 over 15 is 120 over 41 volts. So two different ways to get the same result, just looking at the circuit a little differently. All right,
Dr. Hartman,
yes.
in your schematic above for VR, it kind of hard to tell, but is that's supposed to be 0 minus, not 0 plus, right?
Yes, both of those are supposed to be 0 minus. So if I wrote plus signs there, I apologize. Let me make that more explicit. Thank you for that.
I was also curious about that, so thank you for asking the question.
Yep, I put a plus sign here. Yeah, so we're analyzing at 0 minus. I just put the wrong superscript on those zeros. My apologies there.
No worries. Thanks for clarifying.
All right, so we've looked at these quantities two different ways. We got the same result, so I believe they're correct. Let's move along to step number 2. So for step number 2, we are going to analyze the circuit at t is equal to 0 plus. The moment after the switch changes states. So our switch is now going to be open. So let me look up here, refresh myself to what my original circuit was. So 10.6, all right. So 10 volt source, 4 ohm resistor, 6 ohm resistor. This open circuit here represents our switch. I think this was a 5. Yeah, 5 and then 3 and then 12. Okay. And we're going to do what we did on Thursday. We're going to replace our capacitor at t is equal to 0 plus with a voltage source, where this voltage source is going to have the same polarity as VC at 0 minus. So that was defined as positive on top, negative on bottom, and it will have the same value as well, which is 120 over 41, volts. And here is VR at 0 plus. So we can say from the jump that VC at 0 plus must be whatever it was at 0 minus, which was 120 over 41 volts. Now using voltage division, VR at 0 plus is going to be that 120 over 41 volts times 5 ohms over 3 ohms plus 5 ohms. So 120 over 41 times 5/8. I get to be 75 over 41 volts. Are we okay with that?
Yeah.
All right. So step number 3, analyze the circuit at t is equal to infinity. Again, we don't really need to do this particular step for this particular circuit, but just to get into the habit of it, So at t is equal to infinity, our switch is going to still be open, but our capacitor is going to look like its DC steady state equivalent of an open circuit. So that means that we're going to have our 10-volt source here. I think this was 4, 6, open circuit, 5,
Next one's 3.
3, and then over here to the right is 12. And then my capacitor here is an open circuit where this is going to be VC at infinity, and this will be VR at infinity. And we can see by inspection here that both of these quantities are 0 volts because neither of them, the capacitor or that resistor, are actually connected to the 10-volt source, right? So that switch opening up removed the 10-volt source from the behavior of everything to the right of the switch. Just as a bit of foreshadowing, or not really foreshadowing, because I'm explicitly telling you, after we wrap this problem up, we are going to investigate what happens when we leave sources in, when the switch changes states. So that's why we're analyzing the circuit at t is equal to infinity will actually give us values that aren't 0. All right, so we have a new step number 4, and this is really doing the exact same thing that we were doing, but just putting it in a new context. So what we're going to do now is we are going to determine the time constant for the circuit during the transient condition. So for an RC circuit, during the transient condition, I'm going to finish writing this down. So for an RC circuit, our old step number 4 was to determine REQ and to determine CEQ. That's exactly what we're going to be doing here, because we know that the time constant for an RC circuit is R equivalent times C equivalent. Okay, so we're really not doing anything remotely new. We're just calling it something slightly different that will work for any circuit or any one of these first order circuits. Determine the time constant. So we know that tau is equal to REQ times CEQ for an RC circuit, and I firmly believe that CEQ here is 60 millifarads. If I scroll up here and look, because it's the only capacitance in my entire circuit. So that one pretty obviously needs to be CEQ. Okay. To determine REQ, we need to look at our circuit during the transient condition. So let me draw that out here. So here's our 10-volt source. Our 4 ohm resistor. Our 6 ohm resistor. The open circuit, because the switch is open during the transient condition. 5, 3. Here's our capacitor. There's our 12 ohm resistor. So here's our circuit during the transient condition. We are trying to find the Thevenin equivalent resistance with respect to our energy storage element. So that means I take my energy storage element, in this case, my capacitor, out. And I'm looking in through the terminals behind when I remove that energy storage element. I also need to be looking at a dead network, which means I turn my independent source off. So to me, I see 12 in parallel with 3 plus 5. Or 12 in parallel with 8. 12 times 8 over 12 plus 8 comes out to be 24 fifths of an ohm. Before we move along from here, are you guys okay with that equivalent resistance? Or do you have any questions about that calculation?
No, not necessarily.
Oh,
Not right now, you know.
no, you don't have any questions?
Right. It's like, it's not until I like start working the problems out on my own do I have questions normally.
Okay. All right, so let me, just for the sake of alleviating any possible confusion, let's take a look at this. Okay. So what we're doing is we're applying resistor combination techniques to this thing. So this node right here, I have this node here. This node here. And this node here. And let me label some terminals. So I'm going to call this A, B, C, and D. So I'm trying to find the resistance seen between terminals A and B, right? So if I put A here and B way over here, between A and B directly, I have a 12 ohm resistor. I can go from A to B through node D. So let me put D here. So to go from A to D, I go through the 3 ohm resistor. And to go from D to B, I have to go through the 5 ohm resistor. And then I have that 6 and 4 in parallel. But that's not really between A and B, right? That's between B and some other node, C. So let's just put C down here for the sake of argument. So here's the 4, here's the 6. Since that guy is dangling, it's not part of a closed current carrying path, it shouldn't contribute to my equivalent resistance. So I have 12 in parallel with 8, which is 24 over 5. Okay. So from that, I'm going to have 24 fifths an ohm times 60 millifarads. I'll throw this in my calculator, so times 0.06. I get 36 125ths of a second. And for reasons you will see to be obvious in just a moment, the inverse of this is 125 over 36 per second. And I'm now at step number 5. Which is to plug stuff in to our generic equation. Now, I haven't exactly given you our new generic equation here, but all we're going to do is substitute in our relationship for tau into our old equation. So our generic equation should now be y is equal to y at 0 minus for t less than 0 minus, and y at 0 plus e to the negative t divided by tau for t greater than or equal to 0 plus. So this is the equation that works regardless of whether we have an RC circuit or an RL circuit. We just need to be able to remember how to calculate it. So using this guy, where we will find that VC, that's right, of T is going to be 120 over 41 volts for T less than 0 minus, and it'll be 120 over 41 e to the negative 125 over 36, so that's just tau to the minus 1 t for t greater than or equal to 0 plus. And for our resistor voltage, we are going to have 140 or 150? 150. And then 75. 150 over 41 volts for T, less than 0 minus, and 75 over 41 e to the negative 125 over 36 T volts for T greater than or equal to 0 plus. And I just realized I did not put units there, so let me fix that one. So all of the steps that we developed in our last class meeting are here, but the last two are just in a slightly different context. All right, so before we move on to other things, does anybody have any questions about this example or any of the steps or anything?
So just as a refresher for your generic equations for y, the y0 plus e to the negative t over tau, that's
Yes.
because it's an RC circuit and tau is equal to RC.
So the e to the negative t over tau will be true for any first order circuit. Tau is equal to R times C because it is an RC circuit. So if we had had an RL circuit, this would be the exact same relationship, except that tau would be L over R.
Got it. Thank you.
Yep. Okay, so what we're going to talk about now is the total response of first order circuits. So everything that we've looked at up to this point is what's commonly called the natural response of the circuit. And it's the natural response of the circuit because it's how the circuit behaves without any external influence from voltage or current sources. So if you look at all of the examples that we've worked to this point, our switch has operated in such a way as to remove either a voltage source or a current source from influencing the behavior of the energy storage element. What we're going to look at now is, let me write this down here. So we're going to have our total response, Y subtotal, And it is going to be our natural response, which is what we've been calling y of t, plus what I'm going to call our forced response, y sub f. So the forced response is due to voltage and or current sources being connected to energy storage elements, capacitors or inductors, during the transient condition. So let's look at something very simple here. I have a voltage source Vs, a switch, and now my switch is going to close at t is equal to 0. Here's my resistance R. Here is my capacitance C. This is VC as a function of time, okay? So if we looked at this circuit at t is equal to infinity, this circuit would look like this. Here's our voltage source Vs. Our switch is now closed. Here is our resistance R. Our capacitor is going to look like an open circuit. And here is VC at infinity. Well, what should the value of VC at infinity be?
VS.
Absolutely, just simply Vs. Okay. So we know what the natural response of a circuit like this looks like. We literally have it right up here. Scroll all the way back to the top. So here's our natural response. We just figured out what our forced response is. So let's put things together. Okay. So let me scroll back down. So what we should expect to see is a total response. Actually, let me put this as VC total of time is going to look like VC at 0 minus for t less than 0 minus. I'm going to give myself some room here because there is intentionally a mistake here that I want to talk about. So VC at 0 plus e to the negative t over RC plus VC at infinity for t greater than 0 plus, right? We only add the VC at infinity or our forced response to the bit that's going on for t greater than 0 plus, because t at infinity falls during that time, right? Infinity is later in time than 0 plus. Okay. So can either of you guys tell me what the problem is? It's not obvious.
Have something to do with the VC of infinity?
It does have something to do with that. So what do we know about capacitors? Okay. The voltage drop across a capacitor cannot change abruptly, which means that whatever voltage it had at 0 minus, it has to have the exact same voltage at 0 plus. So if we looked at this expression at t is equal to 0, we have VC at 0 minus here. And then we're going to have VC at 0 plus times e to the 0, which is 1, plus VC at infinity. So this is what's going on at t is equal to 0 minus, and this is what's going on at t is equal to 0 plus.
Which is physically impossible.
Exactly right. So what we need to do is we need to correct. So the problem here is that mathematically, this voltage gets applied at all points in time because it's just a constant value. And so it's slightly skewing our results. So what we're going to do is we are going to simply subtract that value out over here. So we're going to have VC at 0 plus minus VC at infinity. And this corrects everything and makes our expression continuous so that at 0 minus, it has a value of 0 minus, and at 0 plus, it has a value of just 0 plus. The infinity parts wind up canceling each other out at that specific instant in time to make this a continuous function. So generically, then, our expression will become y total is equal to y at 0 minus for t less than 0 minus, and y at 0 plus minus y at infinity, e to the negative t over tau plus y at infinity for t greater than or equal to 0 plus. And what's great about this particular representation is that we can apply it to literally any first order circuit. It doesn't matter if it's a natural response problem, meaning that our sources get disconnected, or it's a total response problem. It'll work just the same, because if it is a natural response problem, y at infinity is just 0, so those two parts cancel each other out. So we can use this generic expression for literally everything if we're unsure of what the distinction between a natural response problem and a total response problem is. But that distinction, in my opinion, isn't particularly difficult to understand. If there is a source left connected, it's a total response problem. If the source is disconnected, it's a natural response problem. All right, so let's take this and let's work an example. So let's do an RL circuit, since we've already done an RC circuit today. So let's say that I have the following circuit. I'm going to have a 2 amp source here. Let's put a 3 amp source here in parallel with a 5 ohm resistor. Let's make this voltage V of t. That's one of the things that we're going to try to find. And then here, I'm going to have my switch. Let's have this switch close at t is equal to 0. Let's make this a 20 ohm resistor. And let's put a 100 millihenry inductor here. So let's define this current as IL, direction down. So this is an example of a total response problem. And I can see that for two reasons. Number one, the 2 amp source is always connected to the 100 millihenry inductor, right? The switch changing states does nothing to remove the 2 amp source from the circuit. So that's one reason why it is a total response problem. Another reason is that the switch closing actually adds the 3 amp source into the circuit, making the 3 amp source also get connected to the 100 millihenry inductor. Okay. So that's why this is a total response problem as opposed to a natural response problem. All right, so our first step will be to analyze the circuit at t is equal to 0 minus. So that means our switch is going to be open. So we're going to have something like this. Here's our 2 amp source. Here's our open circuited switch. Here's our 3 amp source. Here is our 5 ohm resistor over which the voltage V at 0 minus is what we're trying to find. Here's my 20 ohm resistor. And then way out here on the right, I have a short circuit representing my inductor because inductors look like short circuits at t is equal to 0 minus. So how can I determine either of those two quantities?
Nodal analysis.
So nodal analysis would work, but it is utter overkill for this.
I was gonna say mesh, but if nodal is overkill, then that makes me think that mesh is too.
It is indeed.
Yeah. So
We
what, I
use
mean,
KCL.
yeah,
I mean, KCL could be part of it. Let's just think about things here. Okay.
okay.
So let's look at what's going on with the current from the 2 amp source. So it's leaving and it's flowing up. Then it's going to make a right turn. None of it can flow down through the open circuit, so it's going to keep on trucking over here. Now it has a choice. It can flow through the 20 ohm resistor or the short circuit. What's going to happen?
Short circuit.
Yep. So all of our inductor current, or excuse me, all of that 2 amp source flows through the inductor. So IL at 0 minus has to be 2 amps. Now let's look at what's going on with the 3 amp source. This current flows up. It can't continue to flow up because of the open circuit. So all of it has to flow through the 5 ohm resistor. like so. So if the current flowing through the 5 ohm resistor is 3 amps, what's V0?
15
Yep.
volts.
Just from Ohm's law.
Yeah.
So nodal analysis and mesh analysis were absolute overkill for
Yeah.
this particular circuit. Look for the easy relationship first, and if you can't sort things out using them, then move along to nodal.
Okay.
All right, so are we in agreement that IL at 0 minus is 2 amps and V at 0 minus is 15 volts here?
Yes.
Yes.
All right, so now we're going to move along to step number 2. We're going to analyze the circuit at T is equal to 0 plus. So at T is equal to 0 plus, our switch is now closed.
I'm assuming the homework problems are not going to be that easy.
Some of them are, others are not, as is the case with any assignment in this class. So our switch is closed. Here is our 5 ohm resistor. This is V at 0 plus. Here is our 20 ohm resistor. And then we're going to replace our inductor with a current source having the same direction as IL at 0 minus, which was down, and having the same magnitude. Sorry. So IL at 0 plus must equal to IL at 0 minus, which we found to be 2 amps. So we don't have to do any work for that one. The only thing that we have to figure out is what V at 0 plus is going to be. So any thoughts on this one?
Well, let's see. The 3 amps would escape that little mesh there. So then, I mean, maybe nodal, yeah.
So this one isn't as obvious, but I still believe that nodal is overkill. So let me explain why. What I'm going to do here is I'm going to identify my nodes for this circuit. So this is my top node. And this is another node. So what does it mean that there are only 2 nodes in this circuit?
Voltage drop across everything is the same.
Yep. Because everything is in parallel. So we have 3 current sources that are in parallel. What can we do when current sources are in parallel? We can add them together. Well, as it so happens, we have a 2 amp source up and a 2 amp source down, so they're just going to cancel each other out, meaning that all we have left is the 3 amp source. So how am I going to find V at 0 plus now? Well, it's just the voltage drop over the 5 ohm resistor in parallel with the 20 ohm resistor. So V at 0 plus is just going to be 3 amps times 5 ohms times 20 ohms over 5 ohms plus 20 ohms. So 100 over 25 is 4. So if I'm not mistaken, this comes out to be 12 volts. So we could have done nodal or mesh, but once again, looking at things, we got a, in my opinion, easier way to find what we were looking for. Not saying that nodal or mesh wouldn't work, because it absolutely would, but you're setting up a system of equations to do what Ohm's law can do. All right, so any questions about our analysis here?
No, that does, when you explain it that way, that does make sense.
All right, so let's look at step number 3. Analyze the circuit at t is equal to infinity, and this is the first time that we're going to get a non-zero answer. So at t is equal to infinity, our switch is still going to be closed. So we're going to have our 2 amp source here. There's our closed switch. Here's our 3 amp source. Our 5 ohm resistor, over which we're going to have a voltage drop V at infinity. There's our 20 ohm resistor. Because we're at t is equal to infinity, we have hit DC steady state again. Okay, so at t is equal to infinity, our circuit is at DC steady state, which means we replace our inductor with a short circuit. Here is our current IL at infinity. So how can we solve for either of these quantities? And I'll tell you right from the jump, nodal and or mesh is not the easiest way.
Could we do what we had before? It's at infinity.
So
Would IL be 20 then? Or 2 amps, not 20?
So IL isn't going to be just 2 amps.
Would it add with the 3 amps to be 5 amps?
Yes.
Uh,
So let's talk about why.
yeah, okay.
So I'm gonna identify my node.
Mm.
So we really just have one large node, right?
Mhm.
What does it mean when our resistors have the same node on either side of them?
The current's the same?
Well, it means that the resistors are shorted out, right? So they're in parallel with a short circuit.
Oh, yeah,
So
yeah.
that means that none of the current that's flowing in this circuit will be able to flow through either resistor. So all of it has to flow through the short, which is the inductor.
Mhm.
So that's why 2 amps plus 3 amps is 5 amps flows through IL.
Yep, I see that. Okay.
Okay, so what is V at infinity going to be? So how much current flows through the 5 ohm resistor?
5 amps. So 25 volts.
So
0?
it's 0. The current flowing through the 5 ohm resistor is 0 because all of the current flows through the short.
Oh, yep. Okay. Yeah. Yep.
Another way to think about it, the 5 ohm resistor is in parallel with the short circuit, which means it has to have the same voltage drop as a short circuit, and the voltage drop across a short circuit is always 0 volts.
Yeah. 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 Okay.
All right. So now we've analyzed this circuit at t is equal to infinity. Just as a quick mention here, because I think David asked about homework problems and such, this was an actual test question.
Okay.
Yeah, so I'm saying that to tell you guys explicitly, if you know me, and I'm trying to be pretty straightforward about this. I like to make problems that look difficult, but have relatively easy solutions if you know what you're doing. And this is definitely one of those, right? You
Okay.
can see this thing and see like, oh, I could do nodal, I could do mesh. You could, but looking at the circuit, taking your time and figuring out how the things are related lead to easier solutions for each of these steps. Look for things like that before you just use nodal and mesh as what I call a crutch. Okay. So
Yeah.
just giving you fair warning. I am a jerk. All right. So now we're at step number 4. So step number 4 is to determine the time constant for the circuit during the transient condition. So for an RL circuit, tau is going to be LEQ divided by REQ. And because this circuit contains a whopping 1 inductor, I believe emphatically that LEQ is 1 millihenry. So now we have to find REQ. So I'm going to do exactly what I did in our last problem. I'm going to redraw the circuit during the transient condition. So here's our 2 amp source. Here's our 3 amp source. My switch is closed during the transient condition. Here's my 5 ohm resistor. Here's my 20 ohm resistor. And then out over here on the right, I have my inductor. I am going to remove my energy storage element from the circuit. So I take my inductor out. I look in through the terminals, and I need to be looking at a dead network, which means I turn off my 3 amp source and I turn off my 2 amp source. So that's just going to leave behind open circuited terminals. So what do I see?
20 in parallel with 5.
All right, so what's 20 in parallel with 5?
1 over 5 plus 1 over 20, 1 over all that.
20 times 5 over 20 plus 5 is 4. So if we are in agreement that REQ is 20 in parallel with 5, which I believe that to be true,
Yes.
then we're going to have 100 millihenries over 4 ohms. That's 0.1 over 4, which is 1/40th of a second. And so the inverse of tau is 40 per second. And we're now at step number 5. Where we just plug stuff in to our generic equation. So to remind you, our generic equation is as follows. Y total is y at 0 minus for t less than 0 minus, and it will be y at 0 plus minus y at infinity e to the negative t over tau plus y at infinity for t greater than or equal to 0 plus. So for our inductor current, that's going to look like 2 amps for t less than 0 minus. Then we're going to have 2 minus 5, so -3 e to the negative 40t plus 5 amps for t greater than or equal to 0 plus. And for V of t, actually, let me make a, I'll do that in a second. Let's see, we're gonna have 3 times 5 was 15. And then at 0 plus, what did we have? Oh. And I'm just going to make a note here that this represents V at 0 plus minus V at infinity. Similarly, this -3 represents IL at 0 plus minus IL at infinity. I'm not just making up numbers here. We've just done the math to get a single coefficient outside of that exponential function there. All right, so we've now worked an example that illustrates the process of how to tackle total response problems as well. So what do you want to do with the remaining 30 minutes of class time? We'll look at some web work problems. Want to work on the in-class assignment. It's up to you guys.
Can we work problem? Yeah, let's do an in-class assignment.
Okay.
I agree.
All right, so let me find the ICAs really quickly here. So circuits 1, and then I think that's the last time I updated them. And this would be in class assignment number 14, if I'm not mistaken. Okay. So this is the first problem. It is a total response problem. Because this 12-volt source right here never gets disconnected from the inductor, right? So that's why it's going to be a total response problem. All right, so I don't think I left a ton of room here. We could probably make it work. All right, so our goal here is to solve for IL and VR as functions of time. So the first thing that we're going to have to do is analyze this circuit at t is equal to 0 minus. So let's see if we can squeeze that in. Actually, no, that's definitely not enough room. So this is ICA number 14. Problem 1. And let me pull it up on my second computer here, just so that I can see it and not have to drive you guys crazy switching back and forth between screens. All right, so our circuit is as follows. The switch is closing at t is equal to 0. All right. So at t is equal to 0 minus, our inductor is going to look like a short circuit and our switch is going to be open. So here's my 12-volt source on the left. Two ohm resistor, 12-volt source, 4 ohm resistor, short circuit up here representing my inductor. Second 2 ohm resistor, VR at 0 minus. Okay, so what does it mean that my 4 ohm resistor is in parallel with that short circuit?
The 4 ohms, no.
4 ohms, what was that? I'm sorry.
It just disregard it.
Yep. So we get to ignore this 4 ohm resistor. No current will flow through it whatsoever. So what path is the current then taking in this circuit? Well, it's leaving the 12-volt source, flowing through the 2 ohm resistor, then flowing around through this other 2 ohm resistor before flowing back up like this. So that tells me that IL at 0 minus is 12 volts divided by 2 plus 2. So 12 over 4 is 3 amps. Using that information, stylus will write, VR at 0 minus is 2 ohms times 3 amps is 6 volts. So our analysis at t is equal to 0 minus is done. Any questions, comments, or concerns?
No, it's one of those just like basic analysis type of problems like you were talking about.
Yep, absolutely.
Okay.
That's what I like to throw at you guys, and then watch you struggle making mesh work for it. All right, so at t is equal to 0 plus, now our switch is going to be closed. So let's see here. Sorry, the screen's scrolling the wrong direction. There's 12 volts. Here's my closed switch. 2 ohm resistor. My other 12 volt source. Four ohms. I'm going to replace my inductor with a current source having the same direction and magnitude as IL at 0 minus. So that's why it's a 2 amp source directed to the right.
It's 3 amps.
3 amps, thank you. Two ohm resistor there. Here's VR at 0 plus. VR at 0 plus is the only thing that I need to solve for. So, what are you guys thinking?
I see the two 12 volt sources, and so I'm thinking I need to do something with that. I mean, it's like I want to say mesh, right? But I'm trying to get out of that habit too.
So, you could definitely use mesh here and it would make more sense than a couple of the other problems, but I once again believe there's an easier way. So because we have two voltage sources connected together, that to me makes me think about nodal analysis, because that means I'm going to have two effectively free nodes that I know the voltage at. Okay. So what I mean by that specifically is if I put my ground right here, and let me run through and identify nodes. So that's one node. That's a node. That's a node. And that's a node. Let me label some things here. So let's call this A, B, and C. Well, VA is 12 volts. VB is 12 volts. So I really just need to do KCL at node C and I'm done. And this voltage VC is the exact same voltage as the VR that we're trying to find. because VR is going to be VC minus 0 based on the polarities that are indicated on the diagram. So that's going to look like -3 amps plus VC minus 12 over 4. Give me just a moment. My laptop does not seem to be charging for some reason, and it just entered battery saver mode, so I'm worried it might die here in a second.
All good.
Um, that is weird.
And while we're working on this, I've got to leave to pick up my son in about 15 minutes. So if I just hop out, that's why.
Yeah.
Just FYI.
Let me- For some reason, my docking station charger does not appear to be working at the moment. Good thing I have my other thing. All right. So VC minus 12 volts over 4 ohms plus VC over 2 ohms. Equation 1 unknown system. So let me throw that into my calculator really quickly. So let's see, that's going to look like fraction x minus 12 over 4 plus x over 2 is equal to 3. Solve for x. I get VC is equal to 8 volts.
Yeah, the same thing.
All right. And this is VR at 0 plus. Okay. So our analysis at 0 plus is done. Now we're going to analyze it at t is equal to infinity. So at t is equal to infinity, our switch is going to stay closed, but now our inductor is going to look like a short circuit again. My inductor up here. And this is going to be IL at infinity. Here is VR at infinity. So our 4 ohm resistor is shorted out by our inductor again, so it's not going to contribute anything. So what are we going to do?
I'm thinking just I feel like it's just a guess. I was gonna say KVL, but I don't. But only because I'm trying to not use nodal or mesh.
So
Just by looking at it, do we know what VR infinity is? If I'm looking at it right,
I think so. What do you say the answer is?
negative 24 volts.
You are looking at it incorrectly. So let me show you something here. I'm going to identify my nodes. So that's one node. That's a node. That's a node. So what does it mean that the 2 ohm resistor is between the red node and the green node, and the leftmost 12-volt source is between the red node and the green node?
Can you say it one more time?
The 12-volt source is connected between the red node on top and the green node on bottom. The 2 ohm resistor to the right is connected between the red node on top and the green node on bottom. What does that mean?
Gotta be 12 volts.
Yep, that means that those two things are in parallel. So VR at infinity must be 12 volts. Just by looking at it. But once again, it requires you to look at it correctly. So how are we going to find IL at infinity?
We have VR in the 2 ohm resistor.
Yep. So it's just going to be 12 volts divided by 2 ohms is 6 amps, because all of IL will flow through that 2 ohm resistor on the right. None of it is going to branch off and flow through the 4 ohm resistor because it's shorted out.
Could in layman's terms, could I say that the voltage source is like it's coming out, and then the resistance is pushing back enough to reduce the current by half, basically, and that's where the 6 volts comes from for that particular resistor. I don't know if that makes any sense.
The 2 ohm resistor on the right is 12 volts because it's in parallel with that leftmost 12-volt source.
Yeah.
IL is infinity because of Ohm's law, right? So let me show you what I mean here, right? So this is IL, where it's defined. It's going to flow down here. None of it can flow to the left through the 4 ohm resistor because the 4 ohm resistor is shorted out, right? So if any current flowed through the 4 ohm resistor, the voltage drop across the 4 ohm resistor would not be 0, and the voltage drop across the short circuit has to be 0. So all of IL is going to flow down through that 2 ohm resistor.
Right. Yeah.
So using Ohm's law, 12 volts divided by 2 ohms gives us 6 amps.
Yeah. Okay. That does answer my question.
Okay, good deal. All right, so now we need to find LEQ and REQ. So LEQ is pretty obviously 2 henries. So let's see, tau is LEQ over REQ. LEQ is 2 Henries. So we look at our circuit during the transient condition. So here's our 12-volt source on the left. Our switch is closed during the transient condition. Here's our 2 ohm resistor. 12 volts. 4 ohm resistor. 2 ohm resistor. Up top is our inductance. So here's where REQ is, and we need to be looking at a dead network, which means this 12-volt source is turned off, and this 12-volt source is turned off. So what do we see? Well, let's identify our nodes here. This one is a little tricky. So here's one node. Here's our second node. So from this, we can hopefully see that REQ is just 4 in parallel with 2, which is 8 over 6. The leftmost 2 ohm resistor is shorted out, so it doesn't contribute anything.
And we can just see that off the bat because it's connected to the same node on either side of the resistor.
Exactly right.
Okay.
So let's see, 4 times 2, so 8 over 6 or 4/3. Let's try this, 4/3 of an ohm. So we're gonna have 2 Henries over 4/3 of an ohm. Looks like 6/4 or 3/2 of a second. Tau to the -1 is then 2/3 of a per second. And then now we're at the last part where we're just plugging stuff into our generic equation. So IL of T will be 3 amps for T less than 0 minus. 3 minus 6 is -3. Yeah. E to the negative 2/3 T plus 6 amps for T greater than or equal to 0 plus. VR. Let's see, it was up here, 6 volts, and then 8 minus 12. So 6 volts. 8 minus 12 is -4, e to the 2/3 plus 12 volts for T greater than or equal to 0 plus. And we'll wake up my other computer and make sure that I didn't screw anything up by looking at the answer. I did not appear to screw anything up.
The -3 on the E to the -2/3 T for
Mhm.
I. Again, where did that come from? I keep getting lost in that part.
Yep, so that is IL at 0 plus, which was 3 amps, minus IL at infinity, which was 6. So 3 minus 6 is -3. This -4 here is from VR at 0 plus, which was 8, minus VR at infinity, which was 12. 8 minus 12 is -4.
Got it. Thank you.
All right, so we only have 4 minutes left of class and we just wrapped up this problem, so I feel like this is a pretty good stopping point. We also knocked out one of the 2 in-class assignment problems. So yeah, all right, so just really quickly here, what we're going to do on tomorrow's class meeting is we're going to like normally that class meeting would be associated with a lab where we look at a physical RL circuit and RC circuit and figure some things out. We're not going to do that because we're not doing the labs because of the online modality. So all I intend to do for tomorrow's class meeting is to work the in-class assignment problem. It's harder than what I will give you on your exam by a large amount, actually. And then the remainder of the class can be used as a review session for your upcoming test. So bring any questions or anything like that that you have for tomorrow, and I will answer as many as I can until you get sick of listening to me.
So tomorrow we're just doing the in-class assignments on Moodle. There's actually no new material. So this is the end of exam 2.
Yep, this is the last bit of material for exam 2. You're absolutely correct.
For exam 2, will there be 3 days like there were for exam 1?
Yes,
Different
sir.
time? Okay.
Monday, Tuesday, and Wednesday, afternoon and evening, just like exam 1.
Okay.
And you just pick whichever one works best with your schedule and your level of perceived preparedness.
Yeah.
So
Okay.
I'll see most of you guys on Wednesday evening.
Yep.
It is what it is.
Yeah, true.
Yeah, it gives if that's the time that gives you the most, or that's the one that gives you the most amount of time to study. So I fully expect everybody to do it then. But with people working internships, this, that, and the other, I like to give you guys options that will work with your.
I'm sure we'll save most of the questions for tomorrow during the review, but do you expect it to be the same level of difficulty?
Yeah, I mean, same level as same level of difficulty as the previous year's exams, all that kind of good stuff for sure. I mean, the level of difficulty of individual problems changes from iteration to iteration, but like if I throw something particularly difficult for one problem, I usually try to throw a couple of easy ones your way as well, just to kind of balance things out. Generally speaking, the class average for exam 2 is typically the highest for the quarter. I think largely because there's not a whole lot of material on the test. Really, we have Thevenin and Norton equivalent circuits, inductors, capacitors, and transient analysis. Those are the only topics. It is, by its very nature, cumulative, meaning that you're expected to know how most of the stuff from exam 1, how that stuff from exam 1 worked in order to work these problems, but you've gotten more practice and all that kind of good stuff as well. So if the class average for exam 1 is usually somewhere in the ballpark of 60 to 70, the class average for exam 2 is usually in the ballpark of 70 to 85.